Coal seam gas mining has stirred quite a controversy recently, and part of the reason here in Australia is a lack of clarity around what the process entails and what the environmental implications might actually be. I'm here today with Dr. Stuart Khan. Stuart is an environmental engineer at the UNSW Water Research Centre who deals broadly with chemical contaminants in water. Stuart, you recently presented to the New South Wales Parliamentary Inquiry on coal seam gas mining, talking about the implications on groundwater. Can you talk to me a little bit about the key points that you raised?
The concern is when you extract coal seam gas, you also co-extract very, very large volumes of water. And it's those volumes of water that can cause environmental impacts if they're not properly managed, or if accidents happen, if things don't necessarily go as planned. So the coal seams themselves contain lots of chemicals. They contain a lot of salts, which you don't want to mix with drinking waters, and you don't want to mix with surface waters, river waters. But they also contain some very toxic organic chemicals, things like benzene and toluene. One of the risks is when you're actually extracting, you're drilling a well down into the coal seam, you pass through a number of different aquifers, and those aquifers can be very high quality freshwater aquifers. So by interconnecting, you're potentially causing contamination of the freshwater aquifer by the coal seam aquifer. And that can seriously degrade pristine water to a point that is no longer suitable for use.
So you're talking about reservoirs that are actually confined becoming interconnected?
Yes, so many reservoirs, or aquifers as we call them underground, which is an underground reservoir, have what we call aquitards between them, so layers of impervious rock that the water cannot pass through. So we can get quite different qualities of water in different aquifers. The concern then is what happens when we start to drill through those aquitards and we start to mix the waters between different aquifers. And often we don't have a very good understanding of the different pressure gradients, the way waters could move, potential cracking that we can cause in aquitards by major drilling activities.
And this could possibly have implications for drinking water. We're using groundwater and extracting that for drinking water in some cases.
Certainly, especially where you have an aquifer that might be a current or potentially a future drinking water supply. If you damage that aquifer, you've damaged it for good, really.
Now, one of the things you brought up was actually having national regulations regarding this. What are some of the things that government and industry need to do if we're going to see coal seam gas mining operations proceed to ensure that they happen safely and in the most environmentally agreeable way possible?
My concern was that things were happening very, very fast in Australia, particularly in New South Wales, and it's been happening very quickly in Queensland as well. And we started to see a few proposals coming from the big coal seam gas companies in New South Wales. The environmental regulators have very little experience in this area. They don't necessarily know what are the issues, what are the key questions that they need to ask and have demonstrated by the proponents of these schemes, and what sorts of things do they need to insist on in order to make sure that these schemes are designed and managed and operated in an appropriate way. And I was actually getting phone calls from people within the Environment Agency asking me, do I know about issues associated with chemical contaminants in coal seams? I knew very little either. But it made me realise that we have this real lack of knowledge, and we have a lack of a national approach to at least asking what those questions are and understanding how do we do this properly? How do we insist that these things are done properly? So that's what made me initially realise that we really need to come together as a country, the way that we have for drinking water guidelines. We need to get the environmental regulators involved, and we need to get the public health regulators involved. We need to get the industry involved, and we need other stakeholders. We need the community to participate in the development of a clear set of guidelines, a clear understanding of how to do this, what to insist on, what to look out for, where the red flags should be. We don't currently have that. We have it for drinking water, and it's worked extremely well for drinking water in Australia. We have a very comprehensive and consistent framework for managing safe drinking water quality in Australia, and I think that that's potentially a very good blueprint for developing coal seam gas guidelines.
Now, it's obviously very complex because there are so many stakeholders at play. Are you confident that this is something that Australia and the States can work together to actually do and build these safeguards?
We have, when Australia is developing guidelines, and we have many environmental guidelines now, we have a very good track record of collaboration and interacting, learning from other countries, and other countries learning from us, in fact. The World Health Organization drinking water guidelines are very influenced by the Australian drinking water guidelines. So yes, I think that there's a lot to learn internationally, and we're able to do that. But I don't want to make it sound like it's a simple process. I was involved in the development and revision of a few of the national guideline documents, and really to do it properly you need to accept that this is a process that takes 3 to 5 years really to bring everybody together, to sort through the information, to come up with drafts and send those drafts out for feedback and comment, do the revisions, and then really end up with a document that everybody, the industry, the environmental regulators, the community, are happy to work with. It's not a simple process,
no,
but it can be done.
And it can't be a rush job. Like, as you were saying, it's sort of something that you were concerned about. It was moving too quickly at the time. Has it scaled back?
Well, we were moving ahead in the dark. We have the coal seam gas industry putting forward proposals all over large parts of New South Wales and Queensland in particular, with the environment regulators really scrambling to look at what's been done overseas, to learn from what's going on overseas. But having to do that on their own and not necessarily doing it in a consistent way in different places. I think, yes, very much so in Queensland. I know that there has been a lot of movement and a lot of understanding and a lot of change in terms of how they understand the issues associated with coal seam gas and how they will regulate it. But I think that we still have a long way to go. I also think it's important that it's not just the environment departments. I think that public health departments, New South Wales Health, for example, Queensland Health, they need a central role in participating in the guideline development, and I'd really hate to see them left out of the equation.
Mm-hmm. Now, Stuart, you also mentioned the Australian drinking water guidelines, and you say we have a very good track record with that. You were recently involved in some research to actually upgrade those guidelines. Can you explain your role and what you've done and the recommendations that you might have made?
Sure. So the Australian guidelines underwent a major revision in 2004. And since then, the approach has been to keep them updated and to have a rolling revision. So there's a committee on the National Health and Medical Research Council that's responsible for that rolling revision, and I'm a member of that committee. My role on that committee has been to oversee the updating of organic chemical contaminants in water. So we looked at a number of organic chemicals that have increased in profile, we have better understanding of some of the issues associated with them than we did in 2004, and made sure that they were more comprehensively dealt with in the 2011 revision. One of the things that I did try to push that I thought was important was that we have guidelines for drinking water which don't necessarily acknowledge the fact that many of our drinking water supplies are actually water recycling supplies. We have wastewater treatment plants that are discharging water into the environment, into rivers, which flows downstream to a drinking water treatment plant. That water is taken from the drinking water treatment plant and the water is taken from the drinking water treatment plant and used as part of a public drinking water supply. That's fine, but then we also have water recycling guidelines, which are completely separate guidelines for where we do that on purpose, where we actually take wastewater, treat it, and then reuse it for a drinking water supply. I thought it was important to have in the drinking water guidelines an acknowledgement of this unplanned indirect potable water recycling. And so to have that acknowledgement, it actually sends you back to the recycled water guidelines and provides an additional layer of risk management and risk assessment that's required in those circumstances.
Now, water recycling is another thing that you've done a fair bit of research on. And I guess in a country like Australia where you can see extended periods of drought, it's very important to conserve water and manage the resources appropriately. Water recycling is one way of doing this sustainably. Can you maybe elaborate on that idea for us and just the general concept of water recycling and what that is?
Sure. So water recycling is taking water that we would previously have considered to be a waste product and more often than not would have presented challenges as a waste, environmental challenges and cost implications in terms of discharging wastes into the environment. So water recycling is taking that water and saying, look, this is not necessarily a waste product, this can be a resource, and we can take this resource, we can treat it, which involves costs, it involves investing energy into that resource, but we can treat it and we can bring that up to pretty much any quality that we like if we're prepared to invest the cost and the energy into doing that. So we can recycle water for low quality applications very easily, irrigating golf courses and parks and gardens, which we do an awful lot of now in Australia. We're also doing a lot of water recycling for industrial applications, and there are some great examples around the country. Wollongong Sewage Treatment Plant is a good example where they take the water from the treatment plant now, it's treated to a high level through a reverse osmosis process, and it's essentially piped under the fence into the Port Kembla Steelworks, or the BlueScope Steelworks at Wollongong, where it's used in steel manufacturing. And that's important because that's actually a saving of what would have otherwise been the drinking water supply. And it's a major saving from that particular reservoir. More recently, towards the end of the previous drought that we've just come out of, there was a lot of interest in actually recycling water for drinking water purposes. We had two major schemes in Australia under a trial and under construction, one in Western Australia and one in southeast Queensland, where that water would actually be used when needed to recharge the drinking water supplies in Brisbane and in Perth.
Right. Now, there seems to be a stigma, quite a big stigma, and maybe understandably, about this notion of toilet to tap water, so to speak. Now, that's probably not the case, and there, as you mentioned, there are advanced processes to treat this water. But can we actually make this water safe and get it to a standard where it's actually quality drinking water that we can consume?
I think there are two good points there. The answer is yes, we can. We know that we can. Don Bursell, one of the godfathers of water quality and treatment in Australia, is known for saying that we can treat water to any quality we like by filtering it through money. And that is the case. He could have said filtering it through money and energy. And it's true that if you want to invest that amount of money and that amount of energy, you can make the most pure water imaginable from any quality water that you start with. But I think the public perception issue is a real issue, and it's an important issue for us to first of all acknowledge and secondly try to work with. I don't think it's a coincidence that people are turned off by the idea of drinking water that was wastewater. I think that there are probably very good evolutionary reasons for us to be repulsed by the idea of coming into close contact with human waste and human excrement. And so I don't think that that's something that we should just turn our noses up at, so to speak. I think that it's really about trying to get people to understand that yes, that is a natural way to think and that is a natural way to interact with wastewater, but this is no longer wastewater. This really is purified water where we really have removed really all of the toxic chemical contaminants, all of the things that might make us sick, and all of the reasons for why we've evolved and learnt to be repulsed by wastewater. So this is a completely different product here, and I think that's the challenge, to really communicate that point.
Now, you head up a team here at UNSW that's looking at trace chemical contaminants in water, in drinking water, in recycled water, in wastewater. What exactly are you looking for, and how might this research better enable these treatment processes to create clean drinking water?
We have a number of large projects at the moment looking at quite a range of different trace chemical contaminants in water, but many of the projects that we're currently working on are looking at things like pharmaceuticals that people consume, you metabolize partially within your body, you excrete it, it goes down the toilet, ends up at the sewage treatment plant and then is discharged usually into the environment.
Right.
So we have a number of projects looking at those kinds of chemicals that can be measured at very, very low concentrations. And we didn't pay much attention to them 15, 20 years ago simply because we didn't have the technology to measure at those low concentrations. Other important chemicals are the hormones, and the hormones have generated a lot of interest in the last, I guess, 10 or 15 years, where we have seen environmental impacts from human hormones that again are excreted and go down the toilet and through the wastewater treatment plant, but also some synthetic hormones. The birth control pill, ethinyl estradiol, is a very famous case, which is excreted, but it is not well removed by conventional wastewater treatment processes at sewage treatment plants. And so we see quite high concentrations, and when I say high, I mean nanograms per litre, comparatively very small, but high in terms of these are concentrations that are sufficient to have impacts on the environment. And we're seeing some famous cases of fish in rivers have been identified in many countries now, where you expect to have male and female fish, and you expect them to be morphologically different. I'm not very good at picking the sex of a fish, but some people apparently can. And one of the things that you look for is eggs. Female fish, you expect to have high numbers of eggs. Pregnant female fish, even higher numbers, and males, no eggs at all. And there are proteins. If you go down to the cellular level, there are proteins that are responsible for making those eggs. And they're a good assay. If you test the fish for the presence of these proteins, you get an indication of their feminine characteristics or their masculine characteristics. And what we found is where fish have been exposed to some of these chemicals in the environment, you get high proportions of female characteristics. Even the male fish are becoming feminized and are showing these female characteristics. And you can imagine the sorts of implications of that kind of environmental impact if you really destabilise the ratios, the sex ratios between different species in the environment. So that's become a major area of concern in terms of understanding the implications of trace chemical contaminants in ways that we hadn't even realised could happen 20 years ago.
And so they can wreak havoc, these hormones can wreak havoc with fish populations. What other environmental impacts are there, if any? And if this stuff gets into drinking water, perhaps, would there be public health concerns there?
Yeah, that's always the question, and the answer is that at sufficiently high concentration, sure. You can have public health implications of any chemical in sufficiently high concentration. But in terms of wastewater, for a wastewater to the concentrations that we see, we're talking nanograms per litre, to end up in drinking water, the number of chemicals that actually are likely to cause a public health concern are very, very low compared to the number of pathogenic substances. You talk about viruses and protozoa, cryptosporidium and giardia. These are the things that are in sewage that make people sick and kill people. So you would see a major public health impact from those sorts of organisms long before that you would ever detect any sort of impact from these trace chemicals.
Right.
The difference with other species is that many pathogens, many viruses are species specific. They infect humans, they don't necessarily infect fish.
Right.
So the fish can survive with high virus numbers occasionally floating around in the water, but it's the trace chemicals that disrupt their metabolism and interact with their own hormonal systems.
Now, Stuart, we've talked a little bit about drought and Australia being prone to these periods of drought, but this summer we've seen quite a lot of rain. Now, what kind of pressure might rainfall, lots of rainfall, put on sewage systems and, overflows into stormwaters?
Yep. So traditionally a lot. Our sewage systems are often complicated and they're supposed to be segregated from the stormwater system. So you would think that high rainfall should have no impact on the sewage system. But it does. Both the stormwater system overflows and mixes with the sewage system in some cases, especially in very old developed areas, and vice versa, especially where you have cracks and leaks in the sewage system. You get leakage into the stormwater system. So when we have high rainfall, we tend to have high flows coming through our sewage systems. In very high rainfall, the sewage systems overflow, and they overflow into the environment. So instead of having treated sewage in the environment, which is something that we live with and we design our systems to do, we can end up with raw wastewater in the environment. And frankly, the system's designed to do that too. It's assumed to be better to have a sewer overflow and spill raw sewage into a creek than to have the opposite possibility, which is for it to back up and come back out your bathroom sink. So this is a situation that we live with and we deal with, and the only real solution is to have higher capacity sewers and to maintain those sewers in a way that prevents leakage and prevents overflow.
And like you mentioned, in some parts, older parts of the city where the infrastructure is much older, we don't actually have that happening. And you've done some work on the Cooks River, which is a pretty significant waterway in Sydney, and you actually likened it to an open sewer. Can you tell me a little bit about what you found in the Cooks River and discuss that?
So we routinely, with a lot of different projects, go and measure pharmaceuticals in wastewater, and we look at pharmaceuticals coming down sewers and through wastewater treatment plants, and we have a good understanding of the sorts of concentrations that you would expect to see and the sorts of ranges of pharmaceuticals you'd expect to see in sewage. We went out and we had a look at the Cooks River one day with a small project, both during dry weather and during a very major wet weather event in Sydney. And we expected that maybe we'd pick up a few pharmaceuticals during the wet weather event because we expected that you would have sewage overflow into the river, right, and we would be able to detect that. But as it turned out, we picked up very high concentrations of a wide range of different pharmaceuticals up and down the river during both extended dry weather periods and the wet weather period. So that told us that not only are you having the expected sewage overflow during wet weather, you actually have constant leakage. There are broken sewers. Some of those sewers are nearly 100 years old in that area. They break, they're very hard to maintain, they're underground. Most of them, large portions of them are on private property. It's not something that can be easily dug up and investigated and managed on a very routine basis. Right. I think we see evidence that it's time to do something. The level of sewage that's going into the Cooks River is really on par with what we would see in a sewer. The level of pharmaceuticals are on par with what we would see in a sewer. So we know that there are high concentrations of wastewater in there. How to deal with that, how to manage it, is not a simple solution.
And those could have environmental implications, but also public safety implications. You know, you wouldn't want to swim in that river if it's basically
I looking at these trace pharmaceuticals, I mean, they sound very dangerous. There are drugs in the river. It sounds like a major public health concern. But as I say, I look at it really as an indicator of the fact that there is sewage in there, and the fact that there is sewage means that there are pathogenic organisms. There are viruses, bacteria, protozoa in there, and they're the things that will make people sick. So for me, it's an indicator of another greater threat, really, than a direct threat from these pharmaceuticals. The concentrations, again, are nanograms per litre. They're millions of times less than what you would take if you were to drink a litre of water, is millions of times less than what you would take by taking one pill. So sure. I don't see that as being the major issue.
Now, there has been a bit of a drive and a community push to actually get the Cooks River cleaned up, but because it's such a big waterway, it sort of travels through a few different local councils. What are some of the major challenges to actually, getting the situation resolved?
Comparatively, it's not such a big waterway. It's a relatively small waterway. The issue is that it's a very urbanised, high-density area. So if you were to actually say, well, we're going to dig up the sewers along both banks of the Cooks River and try and repair the leaks that have developed over the last century, you're essentially saying that we're going to go into people's backyards, we're going to dig up all of these backyards along both sides of the river. And it's not just the houses immediately adjoining the backing onto the Cooks River, it's the next street and the next street back after that. I really don't see that as being something that can be easily done. Perhaps in the future, when there are engineering techniques for tunnelling through pipes underground, and some of those techniques are used very effectively in some areas, I imagine that this would be a slightly greater challenge in this case, where you have quite a complex network of sewers. But if that technology improves, there might be a way of doing it with less disruption to the community.
Now, you also look at the wastewater treatment process and advanced processes like reverse osmosis. You did find something quite interesting that happened to the trace chemicals after they passed through a treatment process where they reverted from non-toxic form back to a toxic form. Can you talk a little bit about that and some of the interesting things that can happen with chemicals as they pass through these treatment processes?
Yeah, so that was a really quite a unique finding for us, and we were the first to show this concept happening anywhere, was that there's a particular drug called naproxen, which is a commonly taken anti-inflammatory drug, widely taken in Australia. And naproxen comes in two forms, and it's called R-naproxen and S-naproxen, and they're just two chemical differences, and it's a little bit like your left hand and your right hand. They look very similar to each other, but they're not superimposable on each other. So we have kind of left-handed naproxen and right-handed naproxen. As it happens, one form, R-naproxen, is the very safe drug that people use, but the other form, S-naproxen, is very toxic to the liver. And so when naproxen is dispensed as a drug, only one of those is present, and the manufacturing process ensures that the other one is not present. So when you look at naproxen in raw wastewater, you just see naproxen, the one that's dispensed. However, what we found is that after biological sewage treatment processes, we look at naproxen in the effluent coming out of the treatment process, the total concentration has decreased significantly by 90%.
Yep.
But the 10% that's there is about 50-50 R-naproxen and S-naproxen. So we've gone from having a high concentration of something with very low human toxicity to a low concentration of something with quite high human toxicity. What the toxicological implications are on balance, we don't yet know. But for me, that this is a red flag. For me, this says, well, we've only looked at one chemical really. When we've observed this happening with this one chemical in detail. How many other drugs, how many other types of organic chemicals that do exist in this right-hand, left-hand type configuration could be undergoing the same sorts of processes. And what we've identified is that it's a bacterial process. The bacteria in the sewage treatment plant, which we encourage their growth, that we rely on bacteria to break down wastewater. It's their metabolism, it's the way that the enzymes that they're producing and the way that they're breaking down the chemicals can actually lead to this interconversion between the non-toxic to the toxic form.
Mm-hmm. Now, what else are you working on at the moment? Are there any other big projects on the go? I know you're doing plenty. Can you speak about maybe a couple of the big ones?
Sure. I'm involved in a fairly exciting project at the moment, looking at, we know one of the likely or predicted implications of climate change is an increase in extreme weather events. So we're working with some water utilities both in Australia and in the US, trying to get a handle on what are the water quality implications, the drinking water quality implications of different types of extreme weather events. And we don't have a good understanding. What happens when there's a bushfire in your drinking water catchment? What kinds of chemical contaminants? Of course, we would think about things like nutrients, phosphorus and nitrogen, which can end up in the water and lead to algal blooms. But there are other chemicals as well, things like fire retardants, for example, that are sprayed to put out bushfires, can run off and end up in drinking water supplies. We're looking at bushfires, we're looking at extreme rainfall events, we're looking at heat waves, and we had quite a few heat waves in the last couple of years around Australia, and looking at how those heat waves can change the chemistry and change the microbial growth in drinking water reservoirs, and so what sorts of things people have seen. So we've got, and some of our utilities in the US are looking at ice storms and other cold weather events as well, which we seem to have a bit less of here in Australia. So we're working with a large number of utilities, around about 100 different utilities, and developing a series of case studies. What's happened? What was the extreme weather event? And how did that impact A, the raw drinking water quality, and B, the ability to treat the water? Sometimes that is also impacted by extreme events, especially if you lose power. And then developing those case studies and coming up with what we hope will be a valuable online tool for other utilities when they have a prediction of an extreme weather event on the way. How can they prepare? How can they adapt to climate change, and particularly thinking about chemical contaminants in the water and also pathogenic substances if they have growth of bacteria or runoff of overflowing sewers into their water supply. How can they prepare and mitigate against that happening? And then if it does happen, how do they manage it? What's the best approach to making sure that a drinking water incident doesn't turn into a public health incident?
Stuart, thanks very much for joining us today. It was a fascinating chat.
My pleasure, Miles. Thank you.